Okay, now kita go to the how we can understand the hydrogen atom. However, in this chapter, we will skip so many details about the mathematical analysis, but we just take the meaning of every step. So the details will be given for you if you are interested to know details about the analysis, the mathematical analysis. But for this topic, we will just take the conclusion from the analysis. All right. Okay. Now we go to the hydrogen atom, right? So why we need to actually consider the Schrodinger equation? So because there is problem with the Bohr model that we learned in chapter 3, I think, right? At that time we are not using the Schrodinger equation. All right, so this is the model, the Bohr model. That means that we have a nucleus and then we have electron orbiting the nucleus, and then when one electron jump from another, for example from 2 to 3, that means it's absorbed as energy, a quantum of energy from light, and then it will return back and emits a photon of light. So that is the picture of the Bohr model. However, the problem is that why the emission and absorption process is like that. We do not know. At that time, they just fit the model, but they can't explain it very well. And then from the Bohr atom, for the Bohr model, they only can explain atom with one electron. Okay, for example, hydrogen, helium, charge 1, okay, and lithium 2 plus. Okay, so this is 2 proton, this is 3 proton, but it has 1 electron. So when we consider the neutral atom of helium, for example, the neutral atom of helium, it has 2 proton and 2 electron, so it starts to fail. The spectrum that is observed from experiment starts to fail using Bohr model. So for lithium neutral atom, and then as we have many proton in atom, so it will deviate from the formula given by Bohr model. So it is difficult. That means the Bohr model is no longer applicable for atom with more electrons. Okay, and then it also predict wrong magnetic properties of the hydrogen atom. So this is we will look later, because when the hydrogen atom is put into the magnetic field, so it will produce more spectrum lines. So spectrum lines, so it will give more spectrum lines. So Bohr model cannot predict that, and this is called a Zeeman effect, which we will look further into this subtopic later. And then it could not explain electron arrangement in atom. For example, how many electron should be here, how many electron can be allowed to be here. So it cannot predict that, because because of this idea. That means the Bohr model cannot explain more than 1 electron. So if we have 2 or 3 electrons, it cannot explain why, and it fails. Right, and then the electron as a localized point particle is consistent with the more general view. So it means that this is electron and it is orbiting. So we are picturing the electron as a particle, but from Schrodinger equation we know that the particle is wave. So it should be there is a probability to be found anywhere. So it is conflicting the Schrodinger equation. That means it is conflicting the idea that the particle is a wave. So that's why this Bohr model fail. So macam penat kan, kita dah belajar apa-apa fail, gagal pula tu kan, dah penat fikir dekat chapter 3 tu, rupa-rupanya gagal. Dia tak boleh explain for more complicated atoms. Right. However, we still use, because we have a correspondence principle. I think chapter 2 correspondence principle. That means whatever established before should be applicable to the discovery that we have later. So there must be some continuity of the idea. Okay. Then okay, so we go further. So when we want to use the Schrodinger equation for hydrogen atom, we have to convert the coordinate system, because we have x, y, z. So it is not suitable for explaining the hydrogen atom, because the atom is thought to be a spherical. Okay, the spherical. So we need to convert from coordinate. Originally particle, it has a x, y, and z. So we need to transform all these x, y, z into r, theta, and psi. Okay. Okay. So this previously we have separated the function into x, y, and z for in the particle in the box, right? So now we have to transform into the coordinate of spherical coordinate. Okay, so what is the r, theta, and psi? So r is the this is particle, for example. So this is our atom. Okay, so we have our atom, so spherical, and then suppose the electron is here. So we can describe the coordinate of the sphere using spherical coordinate. Instead of x, y, z, we use r, theta, and psi. So r is distance from the center, which is the proton, and then this is the elevation from the z-axis is theta, and this is psi from here. So this is we can imagine this is a plane. Okay, so this is a plane. Apa saya tak boleh lukis. So this is a plane that made by this particle. Okay, so we have this is the plane. So we can recognize that there are three coordinate for each of the variables, and then this r is equal to x square, equal to y square, equal to z square. So this is known, and this theta is equal to this blah 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 blah. I do not know that whether you have learned it in somewhere in mathematics, but you can also derive this, but this is not the focus of this lecture. But you can get the theta is equal to this, and psi equal to this. So this is the transformation from coordinate x, y, z to to the spherical coordinate. And then the potential energy, instead of box, kan sebelum ni we have a box. So that means we have a infinite potential outside the box, and then there is a zero potential inside the box. In a real situations, because we have a proton, actually we have a potential energy which is decaying over the space. So we have so this is proton, and then we have electron. So the potential energy decrease from the proton, so decrease by 1 over r. So that's why we need to use the spherical coordinates, because the potential energy become weak at a long distance from the proton. So we will use this potential energy inside the hydrogen atom. Okay, so we will use this into our Schrodinger equation. So after we transform all of the components of the Schrodinger equation for spherical coordinate, we have something like this. Wow, kan? Wow. Okay, so we have for R, we have for theta, we have for psi. Okay, so this is equivalent to the previous subtopic, which is, let's look here. Okay, so we have the separation between X, Y, and Z. So similar to that, we have that equation over here. So we have three separate variables. Okay. So we do not need to know how can we get this equation, but we know from the previous subtopic that we get those using separation of variables. Okay, so this is a very complicated expression. You do not need to remember because it is open book. So you just to know that there are such a function for spherical coordinate. Okay, so why we need to have this? Because we want to get why we need Schrodinger equation. So there are two things that we want from Schrodinger equation, which is we want to get the wave function. Second, we want to know the energy, right? So always Schrodinger equation will give wave function, and then from wave function we get the energy, and also we get the probability distribution function, because we want to know where is the particle inside an atom. Okay, so how we can get all these thing? We need to apply the boundary condition. So boundary condition is this. That means the wave function of R must be equal to 0 at far away from the proton. So this is proton. So the wave function must be 0 at the far away from the proton. Okay. So and then the value for this angle must be finite. It cannot be infinity. So must be some number, because okay, so you need more imagination. That means this value must be finite. This means 0 to 2 pi. Kan? This one also sama, 0 to 2 pi. Kan, dia tak boleh infinity. Dia mesti memang paling maksimum pun 2 pi. Okay, so this pun maksimum pun 2 pi. Alright. So they must be finite. Finite maksudnya tertentu. Infinite ialah tak terhad. Finite maksudnya had, terhad. Okay. Lepas tu, dan awak tengok ini pun dah kompleks. This is already complex. So to get those things, it is really tedious. We need actually a computer to calculate that. However, finally, the computer will give the answer of the energy inside the hydrogen atom given by this expression. Okay. Then surprisingly, using Schrodinger equation, it is exactly the same as the energy given by Bohr model, right? So that means this Schrodinger equation technique is also in compliance with the previous theory by Bohr model. So it is good enough, right, to get the same expression using Schrodinger equation and using the Bohr model. Alright, so from here actually we can see that there is one dependency of the energy, which is N. N is called a principal quantum number. So this is a principal quantum number. And then from these three wave function separated variables, there are something which existed, which is ML and L. So this, based on the mathematical analysis, these two variables arise suddenly, and this is called later angular momentum and angular momentum number and magnetic moment. So we will look this later, L and ML, what are they. Alright, so we already have this En. Now we go forward. The quantization of orbital angular momentum, which is the L number. So the meaning of this L. Alright. Okay, so this L arises from the analysis of the mathematics here. It arises suddenly. That means L must be occur. But what is L? So after the mathematician did their job, the physicists wonder what is this L. Okay, so what is this L? So this L is called orbital angular momentum. Okay, so so the magnitude of the angular momentum is L times L plus H bar, where this L is 0, 1, 2, 3 until n equal to 1. Okay, so this is the difference between Bohr model, because in Bohr model we have L equal to N H bar, where N equal to 1, 2, 3 and so on. This is in chapter 3. So there is no N equal to 0. That means L cannot be 0 in Bohr model. However, in Schrödinger equation, L can be 0. So that is the one of the main difference between the Bohr model and the Schrödinger equation results. So L can be 0 for the in this Schrödinger equation. So that is the most important difference lah. Okay, so so what is the angular momentum ni? Kan angular momentum ni kalau kita recall balik, kalau kita ada okay, so kita ada elektron kan, and then kita ada proton. Okay, so ini ialah jarak dia R, and then dia ada momentum P kan. So L ialah RP. Actually kan, momentum. Okay, so this is angular momentum lah. Kalau P ni ialah linear momentum, angular momentum ialah pergerakan membulat yang ini. Dia ada dia punya momentum dan dia darab dengan R. So that is a momentum. Alright, so in the visual form, so angular momentum is given by tadi kan, angular momentum sama dengan L plus 1 kan, punca kuasa 2. Okay. Tadi darabkan dengan H bar. Okay, saya tengok balik semula. Okay. So the in the visual form, okay, so electron can be somewhere dekat sini ke kan, sini ke sini, dan dia orbiting lah. It can be around the spherical atom, hydrogen atom. Dia boleh berputar-putar kat situ, dan jarak dan dia punya angular momentum ni boleh sebab dia vektor kan, so dia boleh ada kat sini dan berputar. Okay, macam ni lah, dia boleh berputar kan. Actually bukan macam sorry okay, semula kan. Kalau kita ada elektron, okay, kalau elektron ni berputar gini, ini elektron. Okay, kalau dia putar gitu, okay, dia punya arah L dia macam ni, kat sini. Okay, ini menunjukkan arah angular momentum bagi satu satah yang ini. So kalau elektron tu berputar gini, dia punya L dia arah ni. So elektron ni berputar gini kan, arah sini. Ini so. Okay, jadi macam mana awak nak fahamkan dia punya gambar rajah ni? Maksudnya kalau L0 maksudnya dia punya elektron tu gini lah kan. So around this area. So perputaran, so ini ialah awak punya angular momentum. So dia macam ni. Okay. So kalau kita naikkan sikit begini. Gini. So maknanya ada possibility kan, ada banyak possibility lah kan. So maknanya orbiting tu bukannya macam ni je, tak semestinya tu, sebab dia it can be anywhere. So it can be macam ni ataupun gini. So it can be in 3 dimension kan. So that's why it is represented by this angular momentum. Okay. So that means the electron can be orbiting in any directions where it is represented by this angular momentum vector. But the size of the angular momentum is given by this. Kan? Given by that. Okay. So kalau angular momentum 0, bermaksud partikel tu mungkin berada kat tengah-tengah. Kan dia tak bergerak kan, dia tak mengorbit. So mungkin berada kat tengah-tengah kalau L0. So okay. So this is the visual representation of the angular momentum, and it has a magnitude NH bar, and NH bar ni sebenarnya untuk punca senam ni ialah untuk L sama dengan 2 kan. Untuk L sama dengan 2 kan. Ni kita ambil contoh gambar rajah untuk L bersamaan dengan 2. Okay, so kalau L orbital angular momentum dia L sama dengan 0. Apa nama L itu? L ialah, nama dia ialah orbital quantum number. So L ialah orbital quantum number. So kalau dia sama dengan 2, dia punya gambar rajah sebegini. Dia punya magnitude dia set 6H bar. Alright. So dan bagi setiap vektor ni, kita boleh dapatkan dia punya komponen pada paksi Z. Okay, kita dapat komponen pada paksi Z. Kita boleh dapatkan komponen yang ini. Ini ialah LZ. Ini ialah L. Ini L, ini ialah LZ. Okay, so LZ ni sama dengan berapa? LZ ni sama dengan MLH bar. So kita muncul satu lagi quantum number, dan quantum number tu nama dia ialah orbital magnetic quantum number. Ini akan memberi ada kesannya nantilah. Jadi dia ialah, atau nama lain dia ialah magnetic quantum number. Okay, so magnetic quantum number. Dan kalau kita ambil contoh 2, dia punya magnitude dia untuk angular momentum ialah 2.45 H bar, dan komponen dia ialah 2H bar. Dan kita boleh ukur dia punya sudut ni kat sini. Jadi sudut dia bersamaan dengan LZ. Ini ialah L. Kan? Ini ialah theta. Jadi kita boleh buat je sini formula dia kan. Theta sama dengan apa? Theta sama dengan cos LZ divide by L. Satu sangat lukisan saya ni. Okay, cos. Jadi boleh letaklah LZ ni sama dengan berapa? LZ kan? LZ sama dengan MLH bar. Okay, dan L ni bersamaan dengan so awak boleh ukur lah. Jadi untuk case yang ni, untuk case L sama dengan 2, awak boleh dapat ini, which is 35.3 degree. Dan momentum ni memang dia berputar-putar macam ni. So yang L bar yang ini mewakili elektron yang orbiting in this direction. So awak tengok dah macam complicated kan, tapi that works. Okay, so orbiting electron in this way. Alright, so we have the new quantum number, which is orbital quantum number dengan magnetic quantum number. Okay, kita ada baru dah. Tadi dah prinsip, kita ada 3 lah. 3 quantum number. Jadi macam mana kita nak fahami? Okay, so ketiga-tiganya diperlukan untuk kita tuliskan pada wave function. So wave function kita tu mesti ada dalam L, M dan ML. So ada baru. Okay, sebelum ni kita ada N je. Sekarang kita kena consider 2 lagi quantum number. However, walaupun ada dia punya NLM ni berbeza, tapi dia punya energy dia tetap hanya depend kepada N. Okay, so ini ialah bila oleh sebab ada beberapa kombinasi NLM yang akan memberi tenaga yang sama, maka akan ada degeneration of energy dalam hydrogen atom. Okay, so kita tengok susunan di dalam atom, hydrogen atom. So paling bawah sekali N sama dengan 1 dan L boleh ambil kosong je. Sebab apa Sebab kita ada tadi tu kan, condition untuk tu ialah ke mana tadi? Dekat sini. So L mesti boleh ambil daripada 0, 1, 2 hingga N plot 1. So kalau N sama dengan 1, maksud dia L ialah kosong. Kan? Kalau N ialah 2, awak boleh ada maksimum 2, maksimum 1 which is kosong 1. Okay, itu sebab kita ada kat sini. L dia boleh dapat kosong untuk N1. Kalau N2, kosong dengan 1. N3, kosong, 1, 2. N4 dan berikutnya lah. Okay, bagi setiap L, dia boleh ada satu, which is kita tengok condition yang ni pula. Condition yang ni kan. So, kalau L kosong, dia boleh jadi kosong. Kalau L1, dia boleh jadi kosong, 1, 2, kosong, positif 1, negatif 1. Okay. So, macam ni okay, so tengok sekarang ni untuk state 1 kosong, ML dia kosong. Kalau state 1, dia boleh jadi 3 lah. 1, 2, 3, which is 1, kosong, positif 1. Okay, ini kosong. Yang ini ada 3 states. Yang ini mesti ada 5 state. Okay, so macam tu. Okay, untuk bagi setiap N tu, kita dalam spektroskopi, dalam kajian berkenaan dengan elemen, kita boleh tulis bagi setiap level energy tu ialah sebagai 1S, 2S, 2P, 3S. So, SP ni bergantung kepada L. Okay, so S ni ialah untuk L0, L1, L2, L3. So, L2, which is kat sini L2 sini. So, awak tengok dia D. So, kalau 1, dia ialah P. 1, P. Dan L0 ialah S. Okay. So, bagi setiap N tu, dia ada nama dia sendiri, which is N1 ialah shell K. N2, N3, N4 ialah shell. So, dia punya kerangka lah. Satu kawasan untuk diduduki oleh elektron. Kawasan yang boleh diduduki oleh elektron ialah kalau N1, N2, N3, N4. So, dia punya kawasan tu dah jadi makin banyak lah. Okay. So, however, untuk hydrogen ada satu elektron je kan. Dia paling rendah, dia K lah. Tapi elektron tu boleh lompat kepada N yang lebih tinggi. Jadi, dia akan pergi ke besar. Ke L. Ke M, ke N. Okay. Dan setiap nama tu ada dia punya tu which is SPDF. So dia sebenarnya nama ni tak tahu kenapa nama dia macam tu. Sharp, Principal, Diffuse and Fundamental. So ambil nama depan ni kan. Okay. Lepas tu how many kita buat example kat sini how many hydrogen distinct hydrogen states. States tu maksud dia ialah kat mana, berapa banyak tempat yang boleh elektron duduk. States tu berapa banyak tempat yang boleh elektron duduk. So, okay. So, kalau N3, N3, so L boleh dari 0, 1, 2, dah. Sebab dia kan N-1 kan. Okay, dia ada 0, 1, 2. Okay, macam mana pula dengan ML? Okay, untuk ini, dia ada 0. Untuk ini, dia ada 0, 1, negatif 1. Okay, yang ni pula, ada 5 states. Okay, so ada positif 2, positif 1, 0, negatif 1, negatif 2. So, ada 5. So, 5, 3, 1, jadi ada 9 state. Jadi, kalau kita buat N, L, M, L, kita boleh susun 1, 0, 0, 3. Okay. So, apa tak keluar ni? Apalah kan. 3, 0, 0. 3, 1, positif 1. 3, 1, negatif 0. Mana ni negatif 0? 3, 0. 3, 1, negatif 1. Okey. 3, 2, positif 2. 3, 2, okay, saya dah pening ni kan. Okey. Okey. 3, 2, positif 1. 0, negatif 2, negatif 1. Okey, so ini 2, 2, 2. 3, 3, 3. So ada berapa ni? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okey, pada N yang ketiga ada 9 tempat untuk elektron duduk. Itu maksud dia Okey. Jadi kita dah tahulah rules tu kan. Jadi kita boleh predict lah what will have. Bila ada banyak elektron, kat mana elektron tu boleh duduk, boleh memenuhi kedudukan yang disediakan. Okey. Next kita start dulu lah sebab kita sambung kepada electron probability distribution ni.